sklearnmetricspairwisekernels. Description: the pairwise kernels function calculates the pairwise kernel between samples in two arrays, X and Y. It provides flexibility by allowing the user to choose a specific kernel function and adjust its parameters. This function is particularly useful for tasks involving kernel methods, such as support vector machines (SVMs), where the similarity between data points is measured through a kernel. Inputs: X, an array of shape n samples X. N features representing the first set of samples. It can be a dense array, sparse matrix, or other format supported by the chosen kernel. Y, an array of shape n samples Y. N features representing the second set of samples. It can be a dense array, sparse matrix, or other format supported by the chosen kernel. If Y is none, then the kernel is calculated between samples of X. Outputs: kernel matrix A, 2D array of shape n samples X. N samples Y representing the pairwise kernel values between all samples in X and Y. Steps: the function iterates through each pair of samples from X and Y. For each pair, it applies the specified kernel function, calculating the kernel value based on the features of the samples. The calculated kernel values are stored in a matrix, forming the final output. Metrics: accuracy not directly applicable as pairwise kernels calculate similarities, not predictions. However, the calculated kernel values can be used in subsequent models like SVMs, whose performance can be evaluated using accuracy. Recall not directly applicable as pairwise kernels calculate similarities, not predictions. However, the calculated kernel values can be used in subsequent models like SVMs, whose performance can be evaluated using recall. Precision not directly applicable as pairwise kernels calculate similarities, not predictions. However, the calculated kernel values can be used in subsequent models like SVMs, whose performance can be evaluated using precision. F1 score not directly applicable as pairwise kernels calculate similarities, not predictions. However, the calculated kernel values can be used in subsequent models like SVMs, whose performance can be evaluated using F1 score. Visualization plots. Heat map: the kernel matrix can be visualized as a heat map, showcasing the strength of similarity between different samples. Fine-tune parameters. Metric: this parameter defines the kernel function to be used. Available options include linear, RBF, poly, sigmoid, cosine, pre-computed, and custom kernel functions. The choice of the kernel depends on the nature of the data and the desired similarity measure. Linear calculates the dot product between feature vectors. RBF uses a radial basis function kernel, also known as the Gaussian kernel, which measures similarity based on the Euclidean distance between samples. Poly employs a polynomial kernel, which can capture nonlinear relationships between samples. Sigmoid utilizes a sigmoid kernel, often used in neural networks. Cosine measures the cosine similarity between samples, focusing on the angle between feature vectors. Precomputed assumes that the input arrays X and Y are precomputed kernel matrices. Gamma: this parameter is relevant for the RBF, poly, and sigmoid kernels. It controls the influence of nearby samples and affects the smoothness of the decision boundary. A larger gamma value gives more weight to nearby samples, resulting in a more complex decision boundary, while a smaller gamma value emphasizes the influence of distant samples, leading to a simpler decision boundary. Degree: this parameter is specific to the poly kernel. It determines the degree of the polynomial function used. Higher degree values can model more complex relationships, but may lead to overfitting. Coa 0. This parameter is relevant for the poly and sigmoid kernels. It acts as an offset in the kernel calculation, influencing the decision boundary. Uncertainty methods, not directly applicable as pairwise kernels calculate similarities, not predictions. Challenges and fixes. Challenge 1. Choosing the right kernel. Different kernel functions capture different types of relationships between data points. Choosing an inappropriate kernel might result in poor performance or fail to capture important relationships. Sample use case that resulted in challenge 1. Using a linear kernel for data with nonlinear relationships. Fixes to challenge 1. Carefully examine the data characteristics and choose a kernel that aligns with the relationships present. Consider trying out different kernels and evaluating their performance on the specific task. Challenge 2. Tuning hyperparameters. Parameters like gamma, degree, and Coa 0 can significantly affect the kernel function's behavior and the overall performance. Improper tuning might lead to overfitting or underfitting. Sample use case that resulted in challenge 2. Using a default gamma value without considering data scale and resulting in overfitting. Fixes to challenge 2. Employ techniques like grid search or cross-validation to systematically search for optimal hyperparameter values. Visualize the decision boundary to understand the impact of different parameter settings. Challenge 3. Handling large datasets. Computing kernel matrices for large datasets can be computationally expensive and time-consuming. Sample use case that resulted in challenge 3. Attempting to calculate the kernel matrix for millions of samples. Fixes to challenge 3. Consider using approximate kernel methods, such as Nystrom approximation, or techniques for reducing the computational complexity, like random feature mapping. Explore using specialized libraries optimized for large-scale kernel computations.